Okay. Good afternoon, everyone. So I'm Nassim Corteggiani from Maxim Integrated, chip manufacturer. I'm also a PhD candidate at EURECOM, which is a French graduate school. So today I'm going to be talking to you about Inception, a system-wide security testing for real-world firmware programs. So this work has been done in collaboration with Giovanni Camoretti and Aurélien Francillon, my PhD advisor. Okay, sorry. So embedded systems are present all around us, from home automation to automotive. Among these systems, an important part contains low-power microcontrollers, for example, the ARM Cortex-M3. So these microcontrollers combine hardware and software to perform few tasks or specific tasks. Okay, can you hear me? Okay, try. So why the security of such system matters? There is different reasons for that. First, these systems are increasingly connected, so it may lead to large-scale attacks. Also, it's difficult to patch some part of the code. For example, there is the bootloader, which is often stored on the mask ROM. So the mask ROM is the code, is hard-coded on the chip itself during the manufacturing process, which makes the update impossible. Also, the device may be designed to run offline. They may also contain some sensitive data, such as prevent information or payment information. They may also drive sensitive hardware, such as signaling systems or production line. Recent examples of security issue is the Nintendo Switch, where buffer overflow is present on the USB stack, embedded in the mask ROM. So the ROM code cannot be updated because it's in the mask ROM without replacing the device itself. There is also some other issue, similar issue on the ROM code with the iPhone, for example. An interesting and promising technique to test firmware program is symbolic execution. So it gives a half-path coverage, and it returns test case when a bug is found. So for people who don't know about symbolic execution, just a small reminder. So symbolic execution represents inputs as a set of constraints, and then an interpreter will interpret the code line by line. And each time we'll find a decision or condition that depends on these inputs, these symbolic inputs. We'll fork up the entire program state in two paths. So in this case, for the left part of the if statement, we'll have two paths, one in which we will detect an out of bounds, and on the other one, the interpreter will continue the execution. So at the end, for each path, we have a set of constraints, and by resolving these constraints, we can find a test case, which is useful to replace the bug on the real device. So we started with KLEE. KLEE is a well-deployed and efficient LLVM-based symbolic virtual machine. So it can find memory safety violation, and also it gives a high path coverage, for desktop application. So basically with KLEE, when you have a C source code, you can use C-long to emit bytecode, which is a semantic model for your source code. And then you feed KLEE with this model. And it will return an analysis report that contains bugs and also some precious debug information, such as the files and the line where the bugs are present. So KLEE performs source-based analysis. It's also possible to perform binary-based analysis, but as I will show you, it's different. The detection rate is better with source-based analysis. So if we take these two examples, they perform similar tasks. So they return the expected element of the buffer B1. But there is a difference. On the C test, we have we access to a buffer which is typed and also sized. So we have some semantic information about this buffer. But on the binary code, we access to an address. So we don't really know to which object we do the access. And if we use a lifter for the binary code, like the lifter of S2E or Anger, we can see that the semantic information are the same than the one on the binary code. So we don't know to which object we access. But on the source code, if we use C-long to emit the bytecode, you can see that the semantic information are kept. So we know that we access to B1, our buffer. We know the size of B1 and also the type of B1. These information are really important when you want to detect memory corruptions, because you need to know to which object you access and if you go out of the bounds of this object. So when you have the source code, it's better to perform the analysis on the source code. You can still do that on the binary code, but it's more efficient on the source code because you have types which are lost during the compilation process. And if you perform the analysis on the binary code for embedded system especially, you can have some silent corruptions. So it's corruptions that you don't detect on time, so they will be propagated during the execution. It's mainly due to the fact that embedded systems have low resources, so there is less memory protection than on desktop application. And for more detail, you can see the paper, what you correct is not what you crash, at NDSS 18. So the goal of Inception is to offer a way to test firmware programs without any code modification. But the problem with firmware programs, and especially low-level firmware programs, is that you often have assembly code, which are low-level code. And this code is used for multi-threading support or optimization. It's also used to enable hardware features. So, for example, there is some specific instruction like SVC call. So the first challenge when you want to test a firmware program is to be able to support firmware source code. And firmware source code contains C, C++, assembly, and binary code. Another challenge is hardware interaction between firmware and hardware. These interactions are done through the memory mapping. So, for example, in the source code, you may access to some memory, and this memory are seamlessly redirected to, for example, peripherals or external or internal memories. But this information is not present in the source code. So it's defined in the chip specification. And also, peripherals may raise interrupt signals when a specific task is done. And when the interrupt controller receives these signals, it will stop the execution and then save the current state of the program and then start executing the expected handler. So the second difficulty, is to support this interaction between firmware and hardware, which is not defined in the source code, which is specific to each chip. So we started building a symbolic executor for firmware program. When you have your firmware with C, C++, assembly, and binary, and you use C-long to emit your LLVM bytecode, and then you can use the ARM backend of LLVM to emit your LF binary. So in your LLVM bytecode, you will have a representation of your C, C++, but you won't have a model a representation for your binary and assembly code. So our idea was to replace all functions, all C or C++ functions that contains assembly lines with lifted bytecode issued from the binary code. And then we introduced a glue wire in between these two pieces of bytecode to enable the interactions, because the The IIR obtained from the C++ have a different semantic level than the low IR issued from the LF binary. So the glue IR enable to promote or demote the semantic level when there is a direct interaction between the high IR and the low IR. And then we modified KLEE to support this execution. The Inception Translator supports the ARM Cortex-M3. So we'll now explain how the Inception Translator works. So if we take this source code, we have a C code that calls bon functions, which is an assembly code. So we started with emitting the LLVM bytecode thanks to C-long, and we obtained the IER. Then we use the Inception Translator lifter to emit an LLVM bytecode for the assembly code. And in between, we have the glue IR, which follows the ARM ABI standard that defines how parameters are passed through functions. So in this case, we lower the semantic level by copying the variable A to the register R0 as defined in the ABI. So the merging function, the merging feature, enables allow us to promote or demote the semantic level when you have a high IR that needs to interact with a low IR function. But then we need to allocate some other specific memory for the low IR. For example, we allocate the stack, virtual CPU registers, and the heap. We also need to allocate objects that are only used by the low IR. And an important thing also, we need to allocate at the same location objects defined in the IR and the low IR to enable indirect interaction. We also have to solve some challenge, for example, the indirect calls. So we use the indirect call promotions, which is an redirection table. It only supports the indirect call to the entry point of functions for now. We also had to emulate some hardware mechanisms, such as a context switch, to support supervisor call and also to update specific register value, as it's done on the real hardware. So for hardware interaction, so we have a modified version of KLEE that take as input the mixed bytecode that I presented before, and a config.json that contains the memory configuration and also the test strategy of Inception, and an ELF binary that contains the symbols table that we use to allocate objects. So for each memory addresses, you can define if you want to use a local memory, so it's a memory local to KLEE. If you want to redirect this memory to the real hardware, so it's useful when you want to use real peripherals. You can also use symbolic memory. So in this case, Inception, we consider any possible value returned by these peripherals. So it's another approximation. It's useful also when you want to test untrusted peripherals. So for example, peripherals which are connected to the external world and that can be controlled by an attacker. We developed a custom debugger based on the USB 3 link. This debugger interacts with a real device through the JTAG connection. It's inspired by Avatar, and also surrogates, which is a PCI Express based debugger. We couldn't reuse surrogates because the hardware is not available anymore. But we thank the author for sharing the code with us. It was a precious help. We developed the Inception Debugger with off-the-shelf components, so it's quite affordable. And also we added a feature to forward the interrupts from the real device to KLEE. So this feature has also synchronous mechanisms to keep the state of KLEE consistent with the state of the real device. We made some evaluation of the performance of the Inception Debugger. In this evaluation, Inception was as fast as surrogates, except for some read operation. It's mainly due to the fact that Inception uses the lib USB, which is a kernel land, user land driver. So it performs DMA and also syscall for each USB request, which is quite slow. And surrogates overcome this with custom driver, so there is some possibility to improve Inception performance. However, the main bottleneck of Inception is not really the forwarding feature, but more the execution of bytecode, which is slower than forwarding the input-output. So we also compared the native execution with the execution of some code in Inception. And for the UART, as you can see, there is a small differences between the execution in native on the native device and in Inception. It's mainly due to the fact that the UART application has few LLVM instructions but many redirections, so the redirection is pretty fast. But for wget and ping, there is much more assembly line, instruction, LLVM instruction, so the execution is much slower. We compare also the Inception with, we tested, Inception with the benchmark from what you see is what you correct, what you cross is what you correct. In this benchmark, the author takes the XML parser called expact, and they injected 4 vulnerabilities, each vulnerabilities in the separated functions. And these vulnerabilities are a unique trigger condition. So we played with Inception by replacing this function with low IR. So we basically translate these functions in LLVM IR. And you can observe that the detection rate decreases with when the number of low IR functions increase. So it means that the detection rate is not efficient when you perform the analysis on binary-based code. We also tested the Juliet test suite from the NIST. Inception was able to detect all the vulnerability except for the buffer integer overflow. It's due to the fact that we use an old version of KLEE, so we need to update our KLEE. We perform also some verification to be sure that our lifter behave exactly as the native CPU behave. So we tested 43,000 test case issued from generated from the ARM specification, and we compared the state of Inception with the state of the native hardware by comparing registers value and stack value. We tested also the NIST test suite and also the Clockwork test suite and several demo applications for the STM32 and also the LPC board. We tested also Mbed TLS and several embedded operating systems such as FreeRTOS and MiniArmOS. So to conclude, Inception extends the analysis of firmware program to assembly, C++ and binary code. So there is no need to modify the code to perform an analysis on a system-wide firmware program. It fits well also in a life cycle because with Inception you can test without the hardware, thanks to the other approximation. And also you can test your firmware with FPGA-based design. It's also possible to use the real chip, the Silicium version. It's already used at Maxim Integrating to test ROM code, where it found several bugs. And Inception is open sourced and is available on GitHub. And there is also a Docker. Questions?
Hi, John Criswell, University of Rochester. So one question I have is that you're taking source code which contains inline assembly code, right, and you're translating it to LLVM. Are you doing anything special to model that inline assembly code during your symbolic execution, or are you just treating it as kind of a blob within the other sort of quote-unquote regular LLVM instructions?
So there is, when we lift the code from the assembly or binary code, we didn't instrument the code, so it didn't increase the detection rate for a low-level code.
But that's not quite my question, right? So my question is that you're lifting binary code where you have pure binary code, right?
Yeah.
So you have no source code. You're lifting that to LLVM, right? When you're compiling from source code, there can be inline assembly code snippets,
okay,
right, that are embedded with the LLVM that comes from source code. And so the question is do you actually do anything special for that, like lifting that to LLVM like you do for the pure binary?
Yeah. So when there is a C or C++ function, for example, that contains assembly code, we remove these functions and replace it with lifted code from the binary. So we replace the entire functions with the equivalent obtained from the binary code.
Okay, thank you.
Hi, Yunhan from Baidu. So my question is, how do you compare your approach to S2E with semantic support? So because S2E also lift LLVM from bytecode, but we want to add, to make it know there are memory boundaries, so we can use compile time inserting like synthesizers to achieve that. And how do you compare your approach to that?
So you mean now if I compare Inception to S2E in terms of detection?
Yeah.
So it's quite different from S2E because Inception is based on the source code, but you can also test binary code, but it's less efficient. I mean, with S2E you can still test optimized code and so on, and it supports it will support indirect code. But with Inception it's more limited. The binary support is more limited. You need also some debug information to well merge the C code and the binary code.
Okay, thank you.
Well, I have one question. You tested this out on the proprietary code.
Yeah.
So do we have an example of non-proprietary?
Yeah, we tested also. We tested also FreeRTOS, some multi-threaded application. Sorry, we tested also FreeRTOS with some multi-threaded applications, and also all the demo for the STM32 and NXP board. But on this demo, we didn't find any new vulnerability. We were able to find some previously known vulnerability, but no new vulnerability. Yeah.
Let's thank our speaker again.